Hello everyone, welcome to my number theory lecture. In this lecture we study the division algorithm. We begin with the following two theorems without proofs. First theorem is the so-called the division algorithm. Suppose that a and b, there are two integers with both being positive integers and b is greater than a. Then there exists uniquely two integers q and r with r greater than or equal to 0 less than a such that b equals aq plus r. Actually, this is quite familiar um, to you, right? What it says basically is, when the positive integer b is divided by another positive integer a smaller than b, you know, the quotient is q and the remainder is r. Okay, right. And next theorem is if a and b are positive integers, then the greatest common divisor, that's the notation for the greatest common divisor of A and B, right? And bracket notation means, again, as a reminder, this is the least common multiple of A and B. So the GCD times LCM is same as A times B. Okay, so that's the second theorem. All right, so moving on. So here's a lemma I would like to talk about, okay, which is actually very important, okay, uh, for, in fact, the finding, the greatest common divisor of two integers, okay. To give you a heads up, what it does is, in general, like when you have two small numbers, I mean, you find no problem finding like the greatest common divisor of those two integers, right? But things become very difficult, could become very difficult when A and B, those two integers are very large, the numbers, okay? But this lemma allows us to reduce the size of the pair of integers involved, and the, that will allow us to calculate the greatest common divisor of the original pair more easily. Okay, right. So what it says is for any integers, the a positive, b, c, and k. And if A is given by BK plus C, then the greatest common divisor of A and B is same as the greatest common divisor of B and C. Right, so, to give you the motivation, behind this lemma, let me go to my notepad. Okay, so first, before we talk about the lemma, let us talk about this. Suppose uh, that we have two integers, okay? Suppose that we have two integers, a and b, okay? So both are positive integers and b is greater than a. Well, in that case, then by the division algorithm, okay, by the division algorithm, we have what? There exists uniquely two integers q and r, right? Q and r. Here, like r is greater than or equal to 0, strictly less than a, such that b equals aq plus r, right? B equals aq plus r. Right, so that's the division algorithm, right? Okay, so here, if D equals the greatest common divisor of A and B, okay? So we are going to denote the greatest common divisor of A and B by D. Then D divides A, and also D divides B, D divides A, and D divides B. So D must divide R, right? Because, from here, R can be written as what? B minus AQ. B minus AQ. Okay? So that's a linear combination. Okay? So R can be written as a linear combination of A and B, right? As clearly see. And so, we talked about, some properties of, the division, right? Last time. And so, one of the properties is, if, like we said here, D divides A and D divides A and B, then D divides any linear combination of, A and B. So we see that D divides R. Okay, D divides R. Okay, so the D divides A and D divides R, so this implies that D is a common divisor. Okay, D is a common divisor of A and R, so this implies that the greatest common divisor of A and R, right? That's the largest of all, common divisors of A and R. So obviously, D is less than or equal to, the GCD of A and R. Okay, right. So that's what we have. Now here, since the GCD of A and R divides A, and also the GCD of A and R divides B as well. Why? Because again, B is a linear combination. This is a linear combination of A and R. So obviously, GCD of A and R divides both and R. So it's gotta divide the B as well. Okay, so we got this. So this implies this means that, right, A the greatest common divisor of A and R is A common divisor. Is A common divisor of A and B. A and B. And what that means is, this is a common divisor of A and B. So the GCD of AR has to be less than or equal to the greatest common divisor of A and B, which equals D. So what do we have? We have D is less than or equal to the GCD of A and R, and here we just showed that the GCD of A and R is less than or equal to D. So which means that we have what? D, which is the greatest common divisor of A and B, which is also same as the greatest common divisor of A and R. Okay, right. So in other words, right, yeah, i.e., the greatest common divisor of A and B equals the greatest common divisor of A and R. Okay, so what is so big deal about that? Again, like I said, so the A and B is the original pair of integers that we want to find the greatest common divisor of. Okay, right, and that is it turns out that that equals the greatest common divisor of A and R. R is less than, R is right. So the R is less than B. Okay, R is less than B. A is less than B and R is less than A, so R is less than B, of course, obviously, right? So instead of actually finding, the GCD of AB, we can actually try to find the GCD of A and R, which involves, the smaller integer. So this, right-hand side, right, finding the greatest common divisor of A and R, is easier than finding the GCD of the original pair A and B, right? But it doesn't stop here. I mean, this process can continue. Okay, this process can continue. So, you can actually easily see that the statement that we have here. I mean, the thing we proved it right now. Okay, that is a motivation behind the dilemma I talked about. In fact, you can see that this lemma is the generalization, okay? A generalization of what we discussed just now, all right? Okay, so actually the proof we did, right, can be applied to prove this lemma also. So let's get back to that. To my note, okay? So we have here, so we have more generally, More generally, we have the lemma we just talked about, okay? The lemma for any integers, right? So this is the statement, right? So for any integers for any integers a positive, b, c, and k if they satisfy this condition. Okay, so a equals bk plus c, then the greatest common divisor of a and b equals the greatest common divisor of b and c. Okay, so you can immediately see by comparison, right, the similarity between the previous the statement and also this one here. Okay, so let's prove this. Like we did before, let's let D be the greatest common divisor of A and B. Okay, so the original pair of numbers. Okay, that we would like to find the GCD of. All right. So since proof is pretty much the same, since the D divides A, that means and D also divides B, right? D divides A, D divides B. C can be written as a linear combination of A and B, which is actually A minus BK, right? So D must divide the linear combination of A and B, which is C. Okay, so we have that. Now, since D is a common divisor, common divisor of, in this case, B and C, right? Common divisor of B and C. So D has to be less than or equal to the greatest common divisor of B and C. So we have that, right? Okay, so now for simplicity, let us denote the greatest common divisor of B and C by another letter, C. I mean E, sorry, E. Okay, so since, well, in this case, E divides B and also E divides C, so E must divide any linear combination of B and C, right? In this case, so obviously it's got to divide A as well, okay? So E is a common divisor of A and B, right? E is a common divisor of A and B. So this implies that E is less than or equal to the greatest common divisor of A and B, which is D. So what did this show? Earlier, we have shown that D is less than or equal to this guy, the greatest common divisor of B and C, that equals E, right? So we have shown that D is less than or equal to E. Now we have just shown that E is less than or equal to D. So this means thus we have what? D equals E. In other words, the greatest common divisor of A and B equals the greatest common divisor of B and C. Okay, right. So actually, for practical purposes, here, like what I mean by, a practical purpose is like what, the finding the greatest common divisor. Okay, actually, we don't need this lemma, right? Because this is what we are going to use the previous, the statement, right? Basically, what we are going to use is, the division algorithm, actually repeated application of a division algorithm to find the greatest common divisor of two integers. So we don't actually need that, but that's, a nice generalization. Okay, so going back to my lecture slide, uh, huh, okay, so we're gonna go over an example. Okay, so here's an example. So let's say that A equals 1, 2, 3, and B equals 504. Then, you know, so 504, when you divide 504 by 123, the quotient is 4, remainder is 12. So 504, it can be written as 123 times 4 plus 12, right? So applying this lemma, or actually, the applying the division algorithm we talked about, right? Okay, so we see that the greatest common divisor of 1, 2. Here there's typo. Sorry about that. It should be 1, 2, 3. Okay, so I gotta fix this. But anyway, the greatest common divisor of 1, 2, 3 and 504 is same as the greatest common divisor of 1, 2, 3 and 12. Of course, right hand side, is right, dealing with a smaller number, right? So it's easier for us to find the GCD of, which happens to be the same as the GCD of the original pair, 1, 2, 3 and 504. So when you divide 123 by 12, right, the quotient 10 and the remainder equals 3, right? So 123 can be written as 12 times 10 plus 3. So we can actually apply the lemma again, or the division algorithm, right? So, well, in this case, so by applying, say, let's say this lemma, okay, actually, it's pretty much the same thing. So applying this lemma again, what we have here is the greatest common divisor of 12 and 123 is same as 3, the greatest common divisor of 3 and 12. And 12 happens to be a multiple of 3, so the GCD is 3. So therefore, we obtain the greatest common divisor of 123 and 504 equals 3, right? Okay, so here's something called the Euclidean algorithm. Okay, so here's the theorem. Let A and B be integers with what? Both A and B being positive and B strictly greater than A. So by applying the division algorithm repeatedly, right? You know, the one we talked about earlier, right? Okay, so the process can be applied repeatedly. Then we have the following. So B equals, so AQ1 plus R1. R1 is greater than 0, less than A. And then, so what did, right? And when you divide it, so, well, in this case, what we have here is, maybe I better use actually, my notepad. Okay, so here's the theorem. I'm talking about the Euclidean algorithm. Okay, the Euclidean. Well, nowadays, every time you hear the word algorithm, an algorithm, right? You may think of, a computer. If you did that, you are not actually far off. In fact, this Euclidean algorithm, division algorithm or Euclidean algorithm, those are, you know, actually perfect examples of, a computer algorithms. So, in fact, you can easily implement this Euclidean algorithm as a computer program, right, which I am going to talk about in my next lecture. Okay, so right, so here when you divide the A by B, I mean, sorry, when you divide the B by A, so we have A Q1, so there are two integers, right? Q1 and R1, such that B equals AQ1 plus R1, and in this case, R1 is greater than 0, less than A, right? So from this, what do we know? What we know here is I'm going to use different color. So by also successively, applying the lemma, or actually, we don't even have to mention lemma. the earlier we already discussed in terms of division algorithm, right? So what we know here is the greatest common divisor of A and B equals the greatest common divisor of A and R1. Okay, so like I said before, finding the greatest common divisor of A and R1 is easier than finding the greatest common divisor of A and B. However, their GCDs are the same. Okay, yeah, because again, the second pair involves a smaller number, right? Smaller integer. All right, but it doesn't stop there. We can still continue the process, right? So now we can divide, A by R1. So divide A by R1, then there are two integers, Q2 and R2, such that A equals R1, Q1, Q2 plus R2. So here R2 is greater than 0, less than R1. By the way, originally, like in the what is that? The division algorithm. R1 could be 0. Okay, if R1 could be 0, then we are done. The process stops. Okay. For instance, like R2. If R2, let me explain this first. So, what this means is here, the greatest common divisor of A, R1, in this case, right, in the second step, equals the greatest common divisor of R1 and R2. So again, in this case, finding the greatest common divisor of R1 and R2 is easier than finding the greatest common divisor of A and R1, because these guys involve the smaller integer than the previous pair, right? A and R1, right? But if R2 happens to be 0, then A equals R1 Q2. What does it say? That means R1 is A is integer multiple of R1. So in this case, the greatest common divisor of A and R1 is simply just the R1, right? So this is when the algorithm stops, terminates, right? That's why I use the strictly 0, in case you are wondering. Okay, so as long as the right, so the process doesn't terminate, we can still continue. So the next step, right? So you can divide R1 by R2. Then there are two integers Q3 and R3, such that R1 is written as R2 Q3 plus R3. Here R3 is strictly greater than 0, less than R2. So here at this step, what we have is the greatest common divisor of R1 and R2 equals the greatest common divisor of R2 and R3. Again, the finding the GCD of R2 and R3 is easier than the GCD, finding the GCD of R1 and R2. Okay, so this process can continue. Okay, all the way to, say, r sub n minus 2 equals r sub n minus 1 times q sub n plus r sub n, and here r sub n is strictly greater than 0, less than r sub n minus 1. So at this step, we have, right? So r sub n minus 2, the GCD of r sub n minus 2, r sub n minus 1 equals the GCD of r sub n minus 1 and r sub n. Now, let's say that, so next step, so you can divide, okay, r sub n minus 1 by r sub n. So r sub n, then there are two integers, right? Q sub n plus 1 and r sub n plus 1, but let's say that r sub n plus 1 happens to be 0. Then this is where the algorithm, Euclidean algorithm, terminates, okay? Right? So in this case, like I mentioned before, finally, r sub n minus 1, the GCD of r sub n minus 1 and r sub n equals, because r sub n minus 1 is an integer multiple of r sub n, so the greatest common divisor is r sub n. And so starting from following all the steps, right? So what we have here is that the original, right? So the GCD of the original pair A and B is this R sub n, right? So that's what we have. Yeah, so that's the theorem, which is the Euclidean algorithm. Okay, so let's take a look at the following example. It says computer. No, okay, so that is another typo. I got which I have to fix. Compute. Okay, so compute. Sorry about this. Compute the GCD of 558 and 188 using the Euclidean algorithm. Okay, so that's what the one we talked about. Okay, so we're going to apply that. So we first divide 188 by 158. Then the 188 can be written as 158 times 1 plus 30. Okay, remainder being 30. Then we know that the greatest common divisor of 188 and 158 is same as the greatest common divisor of 158 and 30. But it doesn't stop there, right? Since 30 remainder is not 0. As long as the remainder is not 0, you can continue the process, the algorithm, right? Continues. So we can divide 158 by 30, which is what? 158 equals 30 times 5 plus 8. Okay, since 8 is not 0, right? Okay, so we can continue. We can divide the 30 by 8. So 30 equals 8 times 3 plus 6. And again, we can continue the process. Now we can divide the 8 by 6. 8 equals 6 times 1 plus 2. And again, we can still continue. Now this time we divide 6 by 2. And 6 happens to be a multiple of 2, right? So remainder becomes 0. This is where the process terminates. Since 6 is an integer multiple of 2, so 2 is in fact the greatest common divisor of the original pair, 158 and 188. That's pretty neat, right? Okay, that's pretty cool. Okay, so this is it. I think the good place where we can stop, and I will continue this discussion, uh, uh, in my next lecture. Thank you.